Right, hello everyone. This is my second attempt at recording this lecture. Anyway, so last week's lecture covered the concepts of virtualization. I mentioned to you that any resource can be virtualized. That's pretty much any resource. This could be hardware or software, networking devices, etc., etc. You know that virtualization is a concept where a representation of an actual resource is created to be used by an end user. This allows for resource sharing and it's managed by the virtualization layer. We looked at a diagram which described the architecture of a virtualized environment, and in that context we also discussed the role of the hypervisor. So do you remember the term hypervisor? Yeah, so it's also known as the virtual machine monitor. You should know by now that there are two types of hypervisors, type 1 and type 2. We discussed the different virtualization techniques as well, like things like full virtualization, para virtualization, and hardware assisted virtualization. Right. So in this lecture, it will be quite theoretical. It's an introduction to big data. So you guys are used to working with traditional databases. Now we are going to talk about big data, and sometimes I do compare it with traditional database, and it's easier to understand understand the concepts that way. So yeah, you guys are all used to working with traditional databases to perform processing with structured data and where data sets are manageable. But big data refers to data sets which are extremely complex. It's not like the traditional data, so they're extremely complex and absolutely tremendous in volume. Traditional ways of handling data is not feasible, and it requires additional resources and computing power to process the data sets. We all know that the variety in computer applications and their interaction with the environment produces huge amounts of data, and in many cases it's not even possible to store them on a local server. I mean, yeah, of course, I mean, think about the applications we use these days. The applications are complex as it is, and the data they use is tremendous and it's so complex, right? And in many cases it's not possible to store them on a local server. All right. So just think about the kind of applications you use these days. I mean, like Facebook, other social media, shopping applications, etc., etc. So you do realize that these applications rely on complex input that characterize a range of attributes. But it's not just that. The input is processed to form complex decisions using data analytics, machine learning, and artificial intelligence. One simple example is, you probably have heard of this. A complex data set can be used to predict user behavior or a future trend, right? We all know about the controversy surrounding illegal use of data to influence public sentiments. For example, there have been articles in the news about how data has been used to in some way steer the outcome of an election. Well, that's a part of a larger discussion. We won't go too much into that at the moment. All right. So what we are trying to do is get an understanding of the differences between traditional data processing and cloud-based data processing. As I've told you before, what we do today in terms of applications require a completely different approach and completely different thinking. Um, well, I mean, would you be surprised if I told you that the computer that guided the Apollo lunar mission had instructions and data under less than 80 kilobytes of memory? That's how much it was. The rocket which went to the moon, the lunar mission had less than 80 kilobytes of instruction set, right? And it's less than 80 kilobytes of memory. But imagine organizing a space mission like that these days. obviously a lot of data will be collected on the mission, and it needs to be processed in a way which can result in some useful information. So the data set we're talking about these days is not kilobytes or megabytes or gigabytes. It goes into zettabytes. Yeah, it's so we're trying. Even imagining that scale is difficult. So much data. An aircraft engine, right? An aircraft engine generates anywhere between 10 to 20 zettabytes of data just within 30 minutes of flight time. Think about it. Just within 30 minutes of flight time, it generates so many data. So the question is, how do we process this? How do we process such complex data, such huge amounts of data? All right. A good start would be to acknowledge that modern data sets are huge, and hence we give them a name. And what's the name? It's called as big data. So the lecture agenda will cover those points. Why we have to consider big data now? I think the answer is obvious, but anyway, we'll go through that quickly. I already explained what big data is, but we will go more into the analysis of the applications which use big data, in particular social media networks. Of course, then there's all obviously with any system there's the issue with data. There are numerous security issues and all that. So those have to be dealt with as well. Then we'll go on to looking at big data lifecycle and some basic solutions. And finally, there's something called as the CAP theorem, the CAP theorem, and we'll discuss that as well. All very quickly, because it's a very, like I said before, it's a very theoretical set of slides, pretty self-explanatory. So I'm just going to try and I'm going to try not to complicate things. It's pretty straightforward stuff. So the next few slides, we are going to be like I said, it's going to be theoretical. And if you don't, I might be reading off the slides sometimes, because that's all I can do in terms of the text-based information. There's some synthesis, but most of it is self-explanatory. So let's first look at why we need big data now. I think I already explained it, the nature of the applications we use these days. All right, things which we all use in terms of applications on our mobile phones, on our computers. So this has resulted in an explosion of storage needs. All our favorite applications are extremely complex and generate output based on large data sets. Now, we are all fans of social media networks. I think we all are. We use things like Facebook and Twitter and Instagram and whatnot. And these have very large data sets, right? Just think about how much of the data and applications, think about the type of data these applications use, right? So that's what we got to think about. What kind of data comes in? It's not just straightforward text data. It is things like photos, multimedia, usage patterns, etc., etc. So another thing we have established is data is quite complex. On the other hand, we have the rise of the cloud-based solutions like Amazon S3, which is a simple storage solution, and the development of sensor-based applications like Internet of Things and wearable technology like your Fitbit. So these all generate extremely complex data, and you must know how this data is handled. All right. So there is so you can see one of the bullet points there. There's a huge open source community that supports big data technology. So we all should embrace big data, and we need to know how, as computer scientists, as information technology professionals, you need to know how to handle big data technology, and that's a part of your lab sheets actually. So you look into how Hadoop helps, right, in managing big data. So we need to embrace these technologies and develop our applications to future-proof them. And we need to be efficient in processing complex data and big data sets. The final bullet point says there is a shift to dynamically typed data with frequent schema changes. Now look at this thing, right? It's frequent schema changes. So the frequent schema changes are not the norm in traditional databases. In traditional databases had some sort of a consistency to it. It had a structure. The traditional databases knew what the schema is going to be, what the data structure is going to be. But when we deal with complex data, and when we look for ways to store them, it is likely that the schema changes. And it all depends on the data set and how it expands over time. So we are dealing with a situation where databases these days don't follow a specific schema. All right, they are quite varied, and it depends on how they develop over time as well. So the bottom line is, you have heard me say there are huge data sets, complex processing, etc., etc. Why? Because I've also told you about data explosion. At one point in history, we were talking about terabytes, and we were using traditional relational database systems like RDBMS and data warehousing approaches as well to process such volumes of data. All right, and then there is petabytes, which could be associated with typical content and digital access management systems. And then we were in the realm of exabytes, where typical examples are storage of complex DNA information, stock market information, and data on social media networks, some multimedia streaming, etc., etc. And today, it's very important to note that we are in the fourth industrial revolution, right? The fourth, I've mentioned about the fourth industrial revolution a few weeks ago. So it's called as Industry 4.0. So the Industry 4.0 is based on advanced technologies like IoTs, artificial intelligence, robotics, etc., etc. So what we are trying to say here is we are currently going through a data explosion, and we actually don't know how far it will go. What we do know is that we cannot handle this data explosion like how you would have traditionally handled data. Okay, it requires new approaches, new technologies, right? New professionals, and hence the reason for big data, right? So the big data, the field, the way we handle data is a separate category, okay, which I suppose distinctly which distinctly identifies a set of data, set of complex data, all right, or huge data sets, all right. So let's look at some of the data types we are familiar with. We have all worked with a range of computational technologies, right from PC-based desktop environments to cloud-based systems. The diagram you see there gives you an idea of the levels of data volume handled by different applications. Currently, we are dealing with the red bit in the diagram, which is machine-generated data like sensors and IoT. We can also see from the diagram that even with social media and the social media networks, the data handle is tremendous, and it could range anywhere from petabytes to zettabytes. So it's all about data uncertainty. Okay, like I told you before, we don't know how large the data sets will get. For all we know, this is just the beginning, right? And there may be no limitations to how much data computer systems and data centers can handle. I would want you to observe. I will want you to observe some of the statements in the diagram. It kind of puts things into a historical perspective. So about the developments of data management over time. So there's talk about enterprise data, and there's some information about social media accounts. Then there is a talk about explosion of data, of data networks and sensor networks, right? So all of this adds a lot of uncertainty in how data is obtained, stored, and processed. So the bottom line is, well, we have established that data we handle in the current computing systems are complex like never before. They are huge, they are dynamic, they are complex, they are varied, and most of the times they are inconsistent. We need a name to describe all this, and hence we call it as big data. And as you can see from the definition on the slide, big data are information assets that require new forms of processing to enable enhanced decision making, insight, discovery, and process optimization. So what you have to remember is the result of processing big data could be of tremendous value to an application and to businesses. And in many cases, the data processing needs to be fed into real-time systems and decision making. So we need efficient systems that can handle big data. On the slide there, you can see the 3, 4, 5, 6V model of big data. Each of these models reiterates the features of big data. Look at the 3V model. It talks about variety, volume, and velocity. Variety means big data can be structured or unstructured, or even semi-structured for that matter, or a mix of the above. You can see that the volume describes the quantity of data, in terabytes, etc., huge records. It describes how big the records are and the volume of transactions and the number of files. Then we have velocity, which describes the speed of the rate of data generation and data processing. Like I said before, much of the data in our data set might have to be processed in real time or near time, and therefore any application should be able to batch process the data set. Big data has got 6 properties, which of course is there in the final diagram there, but we'll explain that in the next slide. So here are the big data properties. It's high volume, meaning it's supposed to handle high volumes of data and support large number of clients. When we say a large number of clients, it typically means a global scale, right? So these cloud-based applications obviously cater to millions of users worldwide. So big data processing should be able to manage that. High velocity describes the speed of data in and out, meaning the database must be able to handle data storage and retrieval at rapid speeds. And in many cases, it should be able to match the speed of the real-time systems and time-critical systems. High variety describes the property of big data to accommodate different types of data and the different sources of data. I have said before that data in big data system is more than just traditional data. It should be able to represent complex data structures. For example, the type of data you would normally see on social media. High veracity means uncertainty of data. Veracity means how accurate the data is. It's the truthfulness of the data set, right? The truthfulness of the data set. It's not just about the bulk of the data, but it's also about how trustworthy the source providing the data is. It's about how trustworthy the processing system is. You can appreciate how entire systems built with big data need to be accurate and reliable. Therefore, there should be no compromises in the precision of big data set and how it's processed. Now, it might be difficult to evaluate the accuracy of a big data system. I understand that. So it is quite difficult to evaluate how accurate a big data system is, because it depends on a case by case basis. So in the cloud computing world, usually a system is allocated a data veracity score, all right, and a ranking for data set. What they acknowledge is the veracity may not be as high as expected, but it's still good for purpose. So there is a score, veracity score, associated with data sets. All right, to talk about, to indicate how accurate or how reliable that data set is. High value represents the importance of data from a business point of view. As you can imagine, modern businesses rely heavily on data sets, and they use the data sets to perform vital decisions about their business. And in simple terms, data is money, right? Data is value. That's what it is. And then we have high variability, which means that the data evolves over time, and it's usually not possible to predict the future turn of this data. Hence, we say that this is non-deterministic. All right. If you dig deeper, you will find more big data properties. We will not go into all of them here, but that is something we can probably research. And because obviously, big data is quite a dynamic data set. You might want to think about what other properties it might exhibit. Right, with regard to this slide, there's not much to say really, except that it gives you key values about various social media networks, including the amount of data they typically handle. The reason we discuss social media networks while talking about big data is because social media networks use a lot of AI, machine learning, and data mining based on big data sets. All right. Again, some statistics for you to just go through. It gives you an idea of the number of transactions performed by Facebook. One might say that the growth of social media is well, exponential, I suppose. And yeah, we don't know where this entire area is heading to. It's there are data is getting complex, and how social medias use that data is also getting complex, and not just complex, they're also getting controversial. We know big data is complex. We have established that. And we also know that big data doesn't deal with typical data types. So what type of data comprises of a big data set? Now, if you try to imagine a traditional database, you know what it looks like. But let's think about what a typical social media based big data looks like. So just to give you an idea, what kind of data is on social media, for Facebook, for example, we have that pie chart on the screen. As an example, you can see that the variety of data handled by Facebook is things like photo, link, status, video, etc., etc. But all of this cannot be stored using traditional database. At least it cannot be stored effectively. And even if we somehow manage to store this in a traditional RDBMS, there is no way you can process it to perform any, or rather to get any meaningful information that will be of use to the business. All right. So yeah, like I said before, it all goes down to the point being we need a different approach to handle big data. This slide is self-explanatory, and we can perhaps relate this to our own experiences. Can you? Does that kind of reflect what you do on social media? About 6 hours per day. Is that how much you spend? I don't know. Um, So, well, only you can evaluate if that is healthy or not, but I leave it up to you. All right. But of course, I mean, think about it this way: 6 hours of 6 hours on average per user per day, and scale it to millions of users worldwide. You can imagine how much data is being generated. Okay. Well, you can see a lot of points there which could trigger some debate, but I'm sure you can do that in your own time. So I'm not going to get into that debate, or I'm not going to discuss that right now. But I think on a broader scale, you need to think about addiction online, things like search engine optimization, and of course, I'm sure you are aware of the controversies surrounding social media. Like probably the most recent one I could say is, I mean, about 4 or 5 years ago, like the controversy surrounding the Brexit referendum, for example. So it is still a controversy. I'm not saying it is, that there's a discussion going around it. Um, it may or may not be conclusive, but it's still a controversy. So that's this discussion about how various governments study user behavior online on social media, and they're able to manipulate users to manipulate users in a way they, for example, in an election, they are able to manipulate users to vote in a certain way. So yeah, that's like I said, that's a lot of food for thought, and I will let you draw your own conclusions from all of those. Now there are various issues with the big data, and like with all systems, there is the concern about privacy. I think we are all worried about that. What kind of footprint do we leave behind on the internet? Yeah, which is that's your presence on the internet. Do you know who holds your data, and where the data is stored, and what kind of data is stored, how the data is processed, and how long the data is stored for? So if you go deeply into this, it's truly scary, and that's why we have laws and regulations like GDPR that govern how cloud providers and business providers basically must be transparent in the services they provide and how they handle user data. I have already mentioned about crowd control and manipulation. Machine learning and data mining together have produced valuable combination to predict user behavior. So using AI and machine learning, data mining, etc., we are able to predict user behaviors, mentalities, shopping patterns, affiliations, etc. So you can see how information on social media could be an asset to business. Unfortunately, every coin has two sides, for the lack of a better metaphor, really. And social media and big data together have their own set of disadvantages that impact our everyday life. So you see that word there on the slide, which is talks about oblivion. So what does oblivion mean in context of information? The issue is, how long should data be stored anywhere? Can information be taken towards oblivion? Can it be erased completely? What is the lifespan of information? Is there the right of oblivion on social media? I will let you think about it. I mean, it's a right to be forgotten. Um, so yeah, while you're at it, think about your rights to be forgotten on the internet, and particularly in social media. And perhaps you can think about all of this in context of the current regulations and legal aspects like GDPR. So how much does Google know about you? Um, yeah, not much to say about that slide really. There are some links for you to check out. I won't get too much into this because this merely reiterates what we've already said about opinion manipulation. Some people believe anything. Some people base their lives on social media and internet forums. Perhaps that's the only outlet they have, and perhaps that's their only window to the world. So that's what happens when people are so addicted to social media, and they give so much importance to the information or misinformation on social media. Yeah, so anything can be proven. People often end up believing conspiracy theories and fake news. There's too much dependence on social media, and but sometimes it can cause isolation and delusion. Yeah, just you can check it out yourself. Just search on Facebook for a number of groups claiming that the Earth is flat. Yeah, really. Yeah. So just search on Facebook. So there are many groups on Facebook which claim that the Earth is flat, and it's truly a scary that sometimes science or any rational thinking goes out of the window. Now let's go into the technical issues of handling big data. I say technical when I'm talking about implementation, I suppose. So obviously this is not a traditional database. We know that much. So you cannot store them locally on your desktop. You have to store them on a server. Again, any ordinary server will not be sufficient. Ideally, it has to be a cloud-based data center because the capacity of a single server is limited. Also, a single server may not have the computational power to handle complex data set. Because big data powers time-critical systems and applications, high availability is extremely crucial. What that means is that the data cannot be fixated to one server. There should be a fail-safe mechanism to ensure there is always high availability. Right? That's very important. So there should be no downtime. Okay, there should be high availability of the servers. In terms of design of the database, the traditional ER data model, or the entity relationship data model, which I think most of us are familiar with. If you go to traditional databases, it's all about ER modeling, isn't it? So that ER modeling does not fit the current business models. We are talking about those businesses which work with complex data, and those businesses whose business model cannot traditionally fit into an ER diagram. All right. And one of the bullet points there, one of the yeah, it's about data security, which is always a concern. Just with any system, cloud-based systems, big data systems, all of these have concerns about security. So if you were to go about designing a system for big data management, what would your considerations be? How would you provision for data storage? How about data redundancy? So data redundancy means data is replicated across multiple data centers, right? So how would you account for that? How will you improve the efficiency of data center or a data search and the data access time? So there's lots to think about. And are you able to identify any more issues, any more potential issues that could be problematic in terms of big data management? So there you have it. That's a big data life cycle. The stages are self-explanatory, and you can probably understand this better when you actually start working on a big database like Hadoop. Some of those operations sounds very typical of any traditional database, but the way you perform operations on big data sets are different. With regard to data within a big data set, those are some of the operations that can be performed. We have replicate, share, search, access, cache, index, archive, and delete. Like I've said before, the capacity of a single server is limited. So in most cases, it would be almost impossible to accommodate entire data sets on a single server. In terms of deploying data centers, we have already discussed the scale out model. Do you remember that scale out model? I think it was week 1 or 2. We discussed about scale out model, scale up and scale out. We compared scale up and scale out, right? So I hope you can recollect that. So yeah, so the scale out model, we have instead of having one large server, we could have a number of smaller servers, right? So scale out. Um, so this could add to the computational storage power, and then it becomes easy to distribute a big database across multiple data centers, and with probably more efficient processing as well. And there could be multiple threads of operation on multiple data sets. If you have a single server, achieving ACID is going to be hard to get. Okay, so ACID in distributed data systems represents atomicity, consistency, isolation, and durability. I will let you do some research on what each of those mean. Also, think about how you would achieve that with big data. There are also other problems with querying distributed data, like data aggregation. How do you go about identifying distinct values? How do you initiate joins and merge rows from different databases, right? And what about creating complex queries, maybe like subqueries? I think we are repeating ourselves here. The message is clear. Um, that needs to be high availability. Sorry, I'm just going to shut down my email. It keeps beeping. Sorry. There we go. Oh, yeah, that's fine. Um, so what was I saying? Yeah, so I was talking about high availability of big data storage and processing, and we have already established that performance of the single server is limited. Even if we were able to accommodate a big data set into a single server, think about what would happen if that server fails. There will be a single point of failure and it will cause bottlenecks. As a basic solution, what we could do is data replication. Because the data is replicated across multiple servers, it provides fault tolerance. But it's worth noting that strong consistency among replicas causes bottlenecks. We could also enable parallel processing or distributed processing, design lightweight process that are not too CPU demanding. So yeah, we have discussed about distributed systems, but distributed databases come with a whole set of problems as well. All right. But in anyway, nevertheless, I mean, these offer some of the basic solutions because at the end of the day, it's all works on the cloud. So yeah, uh, so these are just the basic solutions, and these days data centers designs are getting more and more complex and more innovative, I suppose. And there are various measures in place to optimize the efficiency of big data centers. Now, I've told you before, the traditional model of the entity relationship model does not fit big data. It is important to capture the object relational mapping or the ORM rather than entity relationships. I think I've told you before that with big data, we are dealing with the schema-less storage. What that means is that there's no rigid structure or a schema to the type of data we are handling and their relationships. The queries are based on put, get, delete by object identifier. And it's as it says there, if you want to change query, you often have to change the database structure. So big data can be partitioned either horizontally or vertically. Again, this is one of those things you will realize when you start working with Hadoop. When you deal with any big data system, these kind of operations become kind of, I think it's practice, I suppose. It just becomes normal. Things like data partitioning and access. Um, so yeah, so you can split the tables or whatever you want to call them. The data set, I suppose, is the right word to use. So you can split the data set either horizontally or vertically. Okay, um, so so you can see the diagram there. How the data has been split across multiple databases, multiple data sets, and they have the same number of columns. It's been split into two. The benefit of this is that the model scales well for both reads and writes, but the disadvantage is that an application needs to be aware on how the data has been split, right? The application needs to be aware on how the data has been split across multiple data sets, right? So there might be an issue. There might be an issue of transparency here. Okay, so you can decide to split the data set in whichever way you want, but then the application needs to be aware of how that partitioning works. All right. Guys, if it doesn't make much sense at the moment, that's absolutely fine. You just once you start going into Hadoop, even some of the basic operations we'll talk about, things like partitioning and all these operations. So yeah, I think you will be clear once you start doing the practical tasks. Of course, the practical tasks don't cover everything, so I would strongly suggest you go a bit deeper into that as well. The other way of doing things would be vertical partitioning. As you can see from the diagram, 4 columns have been put into one partition and the 3 other have been put into another. So you might be thinking about how this can be updated. Recall that I think a couple of slides ago I mentioned about how objects are referred by object identifiers, object IDs. And you can see that both partitions have got references to the key. All right. So you can see that ARC1 in both tables, both data sets, right? So you can identify a particular piece of information from that data set using the key or the object ID, right? Let's not call it key, we call it object ID. Yes, so you can use the object ID and you can see that both partitions have got the references to that. So it makes absolute sense to partition huge databases where we can identify certain data which are relatively slow changing. For example, in this diagram here, the partition with the 4 columns might not need frequent updates. What do you think? So that looks like a basic information, the things which probably wouldn't change, right? So the name, the description, and the price often don't change. What could change is the stock levels and perhaps when it was last ordered. All right. So it makes sense to split the data set into a part or a set of parts which rarely change and a part which frequently changes. Also think about another case where partitioning might be beneficial. There might be certain elements within the table which might contain sensitive data and they might need special consideration on security. So it would make sense, if you ask me, to put those sensitive columns into a separate partition. So security becomes more manageable in that case. But the issue is join operations might be slower. If you don't know what join is, it might become clear when you start working on Hadoop. But if not, just just look at what join operations mean in context of data sets. All right, join pretty much means that joining data sets. Yeah. Now we come to the CAP theorem, the CAP theorem, right? It describes three properties of a system. Consistency, we have that C stands for consistency, which is about all copies of replicated data having the same value, right? All copies of the data having the same value. Then there is A for availability, which we have discussed before. It describes if the system can run even if certain parts of the overall system have failed. Yeah, so what you're saying is some parts of the system could fail. Nevertheless, there should be some degree of availability in the system. And then we have P for partitions. Network can break into two or more parts, each with active systems that can influence other parts. Now the reason we are discussing this is because the CAP theorem says that for any system sharing data, it is impossible to simultaneously guarantee all of these three properties, right? So out of the CAP, we cannot guarantee all three of them. There have to be compromises somewhere, all right? Having all three would be ideal, would be the best outcome, but the CAP theorem says that it's not possible to have all these three at the same time. So the bottom line is we need to make a compromise somewhere, and you can choose, depending on which system you want to implement, you can choose among the three and decide which works best for the system or which is optimal given the situation. So just to, I was talking about taking decisions, right? Taking decisions on choosing between CAP. So just to give you an example, a traditional RDBMS implement C and A. These are consistency and availability. Very large systems, even with RDBMS, could partition at some point. All right, because of the amount of data it's handling, very large systems, even with RDBMS, they could partition, and this would likely result in things like node failure, network delay. So yeah, it's quite a dilemma really. And compare the last slide with RDBMS to big data systems where it might be necessary to decide between consistency and availability. Okay, yeah, so it's quite similar, but there's quite a few combinations here, but there's some trade-offs, and like it says there, most web applications choose A. So if you've got a cloud system with big data, which is catering to web applications, most of those will choose availability because their business depends on having constant access to the data set. There cannot be any interruptions, and the system must always be available. So a big data system can choose to go to the traditional route. I mean, I say traditional, but yeah, between C and A, or alternatively, they can go to choose C and P. All right. So the P depends on timeout settings. So depending on which applications the big data serves, the design could involve focus on consistency and partitioning. So yeah, like I said before, this is all some of the design dilemmas. When it comes to implementing the CAP theorem to a data center. Relaxing consistency makes it easier to replicate the data and provides better fault tolerance and speed of transactions. On the other hand, relaxing availability reduces or eliminates distributed concurrency control. So yeah, you can slice it however you want, but yeah, there are some trade-offs. So this is the final slide, which gives you some examples of how different systems choose in the elements of the CAP theorem. For example, you can see MongoDB prefers to implement consistency and partitioning. On the other hand, Cassandra prefers to do things by implementing availability and partitioning. So yeah, that concludes this lecture. So thank you.